if I forget to turn on the recording after our breaks, because we will have like 2 short breaks during the day and one longer one for something like lunch, you can like remind me after that. Usually it's like an hour and a half of a training and a break after that. I think Shimon did something similar with you yesterday and 2 days ago. Just a quick question. What time would you like to have the longer break for the lunch? Like about 12 is okay with you? Okay. Oh, there's something wrong with my camera. Okay, I will use this one. If you encounter lags from my side, you can also let me know. So I can like repeat last, let's say 3-5 minutes, or I will try to change the network I'm currently using, but it should be okay. Okay, so I will start by the introductory presentation, like an introduction to machine learning in general. And here you will, maybe I will skip history, but you will get to know some theory, useful terms, and what's the difference, first of all, between deep learning and machine learning. So for the last 2 days. Okay, Shimon, can you? Okay, thank you very much. So for the last 2 days, you were training and doing applications with rules and data. So as data, you were using probably images or data after analyzing your images. And as a rules, you were treating your algorithm. And by combining those two, you received answers. So let's say this image is okay, the results are like positive, negative, and so on. That's what you did yesterday. And in normal cases, it should work. So if everything is like standard and you're analyzing, let's say, nuts, or nut is a bad word, like mechanical parts, it should be quite okay to use standard analysis like by intensity, area, rectangularity, and so on, because you know the boundaries. You know what should be used, what the measurement of the objects are. In case of more irregular objects or something more, let's say, natural, like nuts you can see here, in some cases, using like the standard approach with parameters and standard algorithm formulas, ifs, and so on, will work. But in some cases, they will not. So as you can see, here you have like standard walnut, hazelnut, cashew nut. And by using those parameters and the formula, you were able to more or less classify those nuts. But if they are damaged a little bit, or they don't look like they always do, those parameters will not be enough to properly classify them. You can add more and more of exceptions, but it will just make your program bigger and bigger and much more complicated than it usually should be. So that's when machine learning or deep learning may step in. And as you can see, here, instead of rules, you provide answers. So you as a user can provide answers which are labels. So during the model creation, you are labeling the images. You can either label them as OK, not OK. You can assign some classes. So like in case of our nuts, you can assign a class with the name of a nut to it. You can, for example, check just for the background, for example, if you want. But you are providing answers which are labels and data, of course, once again, so our images to our model. And the model learns rules which help it to tell the difference between our input data, how to properly classify it, how to properly look for some defects, errors, features. And that was basically our training phase, because during training phase, our model is learning these rules. And after that, in inference phase, so basically during using of your model, during program execution, you use images once again, but the model already knew the answers, has the rules, and it's giving you predictions. That's important part. It's not like always 100% sure. You will receive probably something like score or heat map with probability of a score. So it will be like 99% sure that it's classified correctly, or 87% sure there is something wrong with this part of the image. So you will not receive a definite answer, but with certain probability, it will tell that the thing you are looking for is or is not there. That's why later you will see when the deep learning is useful, and as you can probably tell right now, it will not be useful for like measuring, because for that traditional machine vision tools are much better and will give you higher probability of a correct measurement or success. But if we skip the history part, we can go to more theory and how we create the models, what happens inside. So what you have inside are neurons, which receive inputs as weights. So you can have like 2, 3, and more of the weights to your neuron, and after mathematical operations inside of it, it gives the answer here as an y. And in the model, you can have a lot of them. They can connect with each other. They can use answers from one neuron as an input to another, and the network may be created that way. Here you have an example of application, like you have 2 inputs here, which is x and y, so coordinate on our coordinate system. And as you can see, there is a weight of 0 on our x, so and weight of 1 on our y. So that's why the x doesn't really matter in that case, and the line is only y coordinate is used to draw this line, telling the difference between correct and not correct images, or one feature and another. But having different weights, different connections, can help with dividing our data set differently and more complicated. This is like just the linear equation. You can have like more advanced mathematical equations to discover it, or much more complicated mathematical models to extract the features and extract the features and use them later. Here is described the difference between traditional neural networks and deep learning, and it's the approach, because in traditional neural networks, what you saw before, so the neurons were connected with one another. So by preparing your neural network, each pixel had information about other pixels, and the amount of information was so enormous that, as you can see, for quite small images like 640 times 460, it needed about 150 gigabytes of memory. So, I mean, even for today's standards, it's like enormous amount of memory needed for it. So, like, the training and execution could take very, very long. That's why some kind of improvements were needed for it to work correctly. And that's why with the advancement of work on neural networks, deep structured neural networks were, say, invented. The boom started happening about like 20 years ago with NVIDIA cards and architecture. The use of like deep neural networks in machine vision started, I think, about 10 years more or less ago. And what deep structural neural networks did was reduce the amount of data needed for the analysis. And here you can see what it exactly did. So not all the pictures didn't have the information about all the other pictures. It was more focused like locally. We didn't have unnecessary connections. What I described before, so feature extraction. So the model was able to go through, let's say, layers, and in each of them focus on another feature, use mathematical description of the feature to extract, let's say, kind of a circles, focus on lines, on line circles, and so on, the important details exactly. Here you have a simple example of feature selection. So for each layer, the model focuses on something, let's say, different. Here, probably you did binarization of the image, like 2 days ago. So it's like the simple example of what you can extract from the image. Another thing it does is resizing or downsizing the image. So as you can see here, if you downsize the image, you of course lose resolution, but some of the most important details about the image are still there. So even if you downsize, you should still be able to see the defects. It's not, of course, it doesn't work if your defects are like very, very small on huge images. But in general, it's not advisable to like look for like free white pixel defects on such big images. So we can look for features. We can downsize the image, and there is also pooling operation. Is usually connected with downsizing. So we only take the characteristic most important pixels from our image and reduce it into an array of just the characteristic most important pixels here. And the last layer of deep learning could be a classifier, something similar to just the neural networks. You will be able to probably see it in a classification model that we have. So after everything, the last layer will up the score to 1, like average it. So you will not receive, the addition of all your scores will sum up to 1, not to, let's say, 0.5. I will just mention it when we go to the classification. And the like layers can go after each other, and we will have like convolution pooling, convolution like extracting features, and so on and so on. So you can like connect everything into a model. And this is where I wanted to go. So this is a table which will tell you when and what to choose, where you should go with traditional machine vision, where to go with deep learning, and maybe if it's a good idea to connect those two, because in Studio you can use deep learning to extract one feature and traditional machine vision to check it and do some analysis on it. Yeah, that's basically if you need some kind of measurements. So if you need to measure something, usually traditional machine vision is a way to go. Some simple counting problems, also traditional machine vision, like working with blobs, should work in most of the cases. If you are able to properly light the image, your object, extract the features using the mechanical parts of your application, not the software part, it may not be necessary to use deep learning. So before starting with deep learning, you can like ask yourself a question: if you can make the image better, if you can extract the features by yourself, if you can do it in traditional way. If that's not always possible, or if you are not sure that traditional algorithm will help you, you can go to deep learning. Just remember, it's not like 100% reliable. It has the probability as an outcome, so it's not always 100% sure it's of the score, but yeah, but in some cases, it's the only way to proceed with the application. And it helps when it comes to classification of something that's not, let's say, uniform. Usually when it comes to like plants, some organic matter, you can also work with OCR on some weird textures or a background. When the defects are not something you can describe easily mathematically or by simple operations, you can go and check deep learning how it works with it. Now I will explain some basic concepts that I will be using during the presentation, but during like our training, I will also explain them more in depth if needed. So first of all, training sets. So in the data you have probably all on your computers, you will see inside of our data sets, we have a division between training and test data sets. So the training data set is used for the training. The test one doesn't take part in the training. It's just for you to check the results on it afterwards. There is also a validation set. Validation set is also used for the training. Right now, you cannot choose your own validation set. We will allow for it in version 5.4. So in version 5.3, which we are using right now, validation set is being selected automatically from your training set. And this validation set is used during the training to check if the training is proceeding correctly. As for some practices, unseen data. No, I don't think so. I mean, right now it is, but you cannot like because usually I mean, you can select percentages. Like let's say 20% of my training set is validation data. We don't have that functionality, so we are choosing from the training set automatically. In the future, you will be able to select, or you can like leave it blank and we will choose automatically. It will be like up to the user. We don't have like availability. We don't have a way to give you the percentage selection, at least from what I know. So you can like have it unseen and use it right now, or you will be able to select your validation data. You mean it should be like random, but selected from the training by unseen, right? Or that way. I mean, that's what we have a test set for. So yeah, the training phase is like we train on training images and check the progress on validation images from the training set. And we check the work of the model, how it behaves, and if it's working correctly on our test set. Like our, let's say, editor or during our training, test set doesn't take any part in the training process. It's just for the user to check it. The validation is used during the training process to see how it's proceeding. And if the results on the validation data are not, let's say, on par with your training data, it means there is something wrong with it. So yeah, we don't use validation to train the model, but we use validation part of the training set to check how the training goes. I think it should explain it. Okay, so some practices that will be helpful. It's better to divide your images into sets before the training. You can load all the images at once and divide them inside of our training editor. But a better practice is to divide them beforehand, have them in, let's say, directories into training, test, okay, not okay, depending on how you want to use them, and correctly load them into deep learning editor after that. I think one of the most important ones is the second one. So have different objects in training and test set. By different objects, I mean, let's say you're analyzing bananas. So you want to have as many unique images of unique bananas as possible. So we don't want to have just, let's say, one banana, take 100 images of it and put them all in your training and test set. You would like to have 100 unique bananas, take 1 or 2 images of each of them, and divide them into training and test set. If you take more images of your unique part, you should put them all in training or test set. You shouldn't have like 3 images of one part and put 2 of them in training, 1 in test. Because, I mean, it will give you better results, right? Because you will have the same image in training and test set. So your overall accuracy should increase and the results and graph will be great. But after that, in like real-time application, you may see that the model is not performing well. So you may do something wrong accidentally on the step of model creation. So remember to have unique samples in training and test set. The third one, use correct representation. So the most usual case you will have. Of course, if there are some weird cases that are considered okay, you should also include them into your model so it can check it. It has some information about them and it can adjust. But if the border cases are mostly not okay, you should just train on the correct ones. If you want to include the border cases, if you think they are important, you can include them. So that's for the image sets. After that, we have pre-processing. Some of pre-processing options will be available during the training. So you will be able to downsize the image or go from color to monochromatic. But you can also do so before putting images into deep learning training. So if you think that you don't need color, don't use color, use monochromatic camera. If you think you can reduce the size, you can do it after image acquisition, for example, but you can also do it in the model training. It's up to you, but you can prepare the image before putting it into deep learning. The most useful one is usually locate objects. So you can locate your object, crop the image, and position your object correctly. So if you reduce the amount of data deep learning receives, so in that case, we will be reducing the rotation of our object, right? It will be better and easier for model to train. So from the pre-processing, we have in editor, it's downsizing and going to monochromatic image. But from the one you can use is like locating the image earlier, cropping, properly preparing your data set. Another thing is a concept of tiling. You have kind of an impact on it. On some of the models, you will see something like feature size or patch size. It will be represented as a square in the top left corner, or if you change some options, it will be a grid, a squared grid. Tiling is used for the training mostly. It will cut images into tiles and send them into batches into the GPU for the training purposes. And the size of the square is a tip for you. How big is the tile? Or more or less how big is the tile, because the feature size and tile size are not always the same. They may differ a little bit. But it's kind of an indication for you. And if you take a look through this square, you should be more or less able to see the defect. It's something like, let's say, a window or a keyhole. If you take a look through and you are able to tell the difference between correct or not correct part of the image, it's an indication that your feature size is correct, is of correct size. There is also epoch in training, epoch probably, epoch in training. So it's like a training, let's say, step. So taking images from the training set, putting into batches and sending to GPU. And you have multiple epochs during your training process. At the end of each of them, you will see the training graph progress, and you can stop the training in any time to like save the model, see the results. Another thing we have you can use during the training or before the training are augmentations. They create artificial samples. So if you don't have a lot of images, you can use augmentations to create some variables in pixels or some geometrical shifts to the image to add artificial samples to your training set. They are very useful, but you have to be a little bit careful when using them. And like the most important thing you need to remember if you want to use them is only select a range of augmentations that may happen during your, let's say, program work. That may happen in real time. So if you have your object positioned correctly, don't select like rotations by 90 degrees. You can add like 3 degrees of rotation, 2 degrees of them, but not 90 degrees of rotation. If you have stable lighting, don't add like 20% of brightness variation. You can add like 2 or 3. So you need to like remember not to overuse them or to incorrectly set some ranges. But if you add some of the augmentations, it will greatly increase your training set and should make the results better if you don't have enough of the images. If you have a lot of images, you don't have to use them, or you can just select 1 or 2 of them to add some, let's say, noise or something like this. And that's how the training process look like. So first of all, you have pre-processing. So parameters like like the network type, like the feature size, like downsizing, going to monochromatic. And after the pre-processing is used on all the images, you go into the training process, which was like preparing batches using augmentations if you've set any, adjusting network, and going in a loop once again and once again. And after finishing, it will prepare the results. And depending on the model, you will see like heat maps, classes, just true or false, or a score. It depends on what tool you will use. Here is also a graph. I mean, you want to go into as precise and accurate model as possible. So it's rather like explanation on what precision and accuracy is. Mostly after the training, you will see like accuracy, and it means how many good and bad samples were correctly classified. Basically, if you see accuracy around like 95 up to 100% or 99.9%, it means that your model is correctly trained, or that you have so many similar images that it was correctly trained. But if your like data is properly managed into data sets, you did everything correctly, 100% accuracy should be the way to go. If you have more classes in your models, it may happen that you like go to 93, 94% accuracy. It's like normal because of the way the error is being calculated. The more classes you have, the lower highest score is achievable. It's not usually possible to achieve the highest possible accuracy if you have like 3, 4, 5 classes in your model. You will also be able to see this kind of graph after your training. It's the F1 graph. There are also like 4 more of them. But what's important for you is this curve and where this point here is. The green one is a result of your training set, and the blue one was validation, if I'm not mistaken, or the blue one was your test set. We can check it later, but what you want to see is something like this. So the closer you are to the top right corner, the better your results overall should be. So if you see a curve similar to this one, it means it was probably trained quite good, and the results should be nice. In some of the tools, you will see a confusion matrix. So if the actual class was correctly predicted as the actual class. And as I told you, you can see accuracy here because one hazelnut was incorrectly classified. But you will see that kind of confusion matrix. And if you switch between training, test, and all sets, it should also change and see just the results on the set you've selected. And I think it's the last thing, is the training progress window. Not all of the tools have it, but most of them. And on the y-axis, you will see either error or accuracy. So if there is an error here, you want to go as low as possible. If there is accuracy, you want to be as close to the top as possible. You will see 2 or 3 lines because you will always see training line, which is the blue one, validation error, the yellow one. And if you are doing like 3, 4, 5 repetitive trainings, you will also see a gray line, which indicates how the previous or your current model behaved in the same time of your training. If you see a behavior like this, so your training and validation curves are apart from each other, it means there is probably something wrong with your model. The reasons may be several, but probably you should like stop the training and check if your data is correct, if you correctly divide it into data sets. Maybe you can change some parameters. Maybe you are training too long or too short. There is no like one definite answer. You need to like take a look and check and see what may help with your training and results. Okay, that's for the introduction. Do you have like any questions about it? Okay. I don't see any. So I think we can go to first of our tools, which is anomaly detection. I will start with presentation once again, but after that we will go to the practical part of the training. So detection of anomalies or anomaly detection is an unsupervised deep learning tool, or how some of developers like to call it semi-unsupervised deep learning tool. It's the tool that needs the lowest amount of iteration from the user. What you have to do is prepare a data set and label images okay and not okay. That's basically all your work. I mean, aside from choosing correct training parameters. But for the dataset creation, that's all. We currently have two main tools, which is anomaly detection 1 and 2. One was our older algorithm, one of the first we created like 6 years ago. But because it was still useful, we left it. But right now we usually use anomaly detection 2 for our inspections. And you have two approaches there. One is one class classification, and another is golden template approach. And the workflow of training the model is the same for all of our networks, but I will explain at least it for the first time. So first of all, as I mentioned, you should load and label training images. If you have it already divided correctly, it should be a quick work. After that, you can also load test images. It says optional because you don't need your test images during the training. You can check your model on test images during, let's say, your inference phase. You can also do so. But if you want to have some parameters and see how exactly your model behaves on your test images, you should add them to your to your data set in the deep learning editor. Also, you can do this step as a last one. So if you already have your model trained, you can add more images, label them as test set, and you can run your model on those images after the training in the editor. The third step is setting your parameters. So like I mentioned before, you can set the main parameters and some augmentations. You can reduce region of interest. It's helpful if you have like an image with, let's say, 300-400 of annotations. So you can reduce the region of interest and annotate just, let's say, 50 objects, not 400 of them. And yeah, if you didn't position your object correctly, it could be helpful to reduce the region of interest just to your object. And the last step is analyzing the results and running training once again if needed. And this is what you will see after you open Deep Learning Editor. So you will be able to load your images here on the left. Just below them, you will see training parameters. Here at the bottom, there's a cog icon. It's a model history. So if you trained your model, let's say 5 times, you don't need to be afraid that your last model is lost. All of them are kept in history, and if you want to go back to your model, you can go there, right-click on the model you want to select, and switch to it. In the history, there is also like accuracy of the model, so you can see which one was the best, and you can also remove your unneeded models from there. Here at the bottom, there is a Start Service button. For the training, you need to run the service. So if it's offline and you will try to run the training, you will see a pop-up that you need to turn the service on. In the middle, you will see the preview of your currently selected image. Just above, you have 3 steps of the workflow. So the first one is what you can see here. The second one is selecting region of interest. And third one will be selected automatically after the training. You will go to training results page. To the right, you have results analysis. So after a successful training, you will see the results there. You can analyze them, and based on the analysis, you can choose whether to keep the model or not. Here you can see the second step. As I mentioned before, you can reduce the region of interest. For this tool, so anomaly detection, the region of interest is the same for all the images. Also, all the images have to have the same size. So there are some restrictions. So that's why if you use this tool, it's a good idea to use location first. I mean, not in the case of textiles, but if you are looking for, let's say, an object and want to check if it's correct or not, it's a good idea to locate it first, crop this object, do the image of the same size, and after positioning it correctly, you don't have to change the region of interest, so you don't have to use this step at all. Yeah, and important thing here in this model, at least, you will not be able to change the region of interest from the level of studio. In other models, it's possible. In anomaly detection, what you set here will be used for your model inference phase. And here you have all the training parameters, which you can see in anomaly detection. I think now they're a little bit different, but you will see the main parameters usually at the top, like feature size, sampling density, something similar to this. You will see pre-processing also at the top. It will be convert to grayscale and or downsample. Just below, you have augmentations. And below the augmentations, you have stopping conditions. So you don't have to wait for the model to stop the training. You can, let's say, select it will stop after 25 iterations, or let's say 10 minutes. If you select more of them, the first one that will be met will stop the training. Also about the augmentations, we will not be using all of them on edge images. It's rather like a set of available augmentations or changes that we can but don't have to use. So in case we are using augmentations, we may, let's say, use just the rotation, but let's say we'll select 37 degrees and scale of 101. So they are like a brackets, the maximum range we can choose from, but we do not have to. If you hover on augmentations or other parameters in Deep Learning Editor, you will see the explanation. Here is the simplified one. But what they do is like rotation can rotate your image. Flip up, down, and left, right is like a mirror. So if you put a mirror, up, down is at the top, it will like flip your image like this. And left, right is like this. Translation, we discovered lately, like a few months ago, is not working correctly. So you should avoid choosing that augmentation. In the 5.4 version, it will be completely removed. Scale is upsizing and downsizing your image by a percentage. Shear, vertical and horizontal angle is like tilting. So instead of this line, let's say you will have something like this. And random noise and luminance is changing the brightness of pixels or adding some noise pixels in the image. And Gaussian blur is specifies the radius of Gaussian matrix that blurs the image. So if you select 1 there, you will have a 3x3 matrix. If you select 2, you will have 5x5. Basically, you will just blur the whole image if you select it. And you will see either this kind of training progress, so with the error here, a number of iterations on the x-axis, or you will not see the training progress at all. I mean, you will just see a bar. Depending on the deep learn detect anomaly tool you choose, one of two options will be there. So if you see this kind of window, you will be able to tell by looking at it if the validation training errors are close to each other or far apart. If you will not be able to see this kind of training progress, you have to focus more on the results of your training. And this is one of the examples we will try in a minute. And I think, yeah, we have also some use cases at the end. So this is one of them. We had to inspect the inside of a sushi box if all the parts were already there. Using anomaly detection, you are not able to, let's say, tell which part is missing, but you can see all the defects here. So I think some part of other meal went here, and there is lack of one of the ingredients here, and you will probably receive a very high score, because the higher the score, the closer to, let's say, not okay you are in this case. And if the image is judged as false, you can, let's say, proceed later in your application and send, let's say, not okay information to the PLC and remove this box from the line. And when it comes to inspection time, here it was below 100 milliseconds per image. But the inspection time depends on your hardware, if you want to use GPU, CPU, and how, let's say, big your images are, what parameters, the main parameters used for the training. It really depends, but usually the higher complexity of the model you choose, usually the slower the model will be. That's like the general rule. So the model with complexity, the one or the lowest one you have, will be faster than the model with the highest complexity. But usually you will trade off some accuracy. So if there's a way of selecting complexity in a model, I will tell you to go with the default one, it depends on the model, but I will tell you to stay with the default one for the beginning, or I will tell you to stay with the lowest possible one. Yeah, that will be all. And I think we can go to the practical part of this training. I will give you some more tips as we go. But first of all, you can turn on your studio. And it's a good idea to save your program first, because during model creation, if you've already saved your program, your model will create in the same directory that your program is. If you do not save your program first, you will have to select the directory of your model. So it's better to make our work easier. I will save it. Just give me a minute. I need to find the path to my directory. Okay, so I will save it in training, deep learning programs, and let's say first one could be maybe caps. So I will name it caps because those will be the images we will be checking right now. So I will just save it. And if we did so, we can go to our training images. So if you have all the training images here, there is the second directory, caps, anomaly detection. If you open it, you will see the division into training and test sets described. But we can go, let's say, to our training set to see how they look like. You can select one of them and take a look at the images. So here is our object of interest. And as you noticed, there is a green dot at the top left corner. So we will have to remove it by adjusting region of interest. So it will not affect our models, because in the not OK sets, there should be a red dot here. Okay, but if we have the images, we can leave them for now, and we can go and add our filters. So how to exactly create the model, how to open the editor. So the first way to do so is from Aurora Vision Studio. So if you've saved your program already, you can go to the left, select your toolbox, and there should be a tab, Deep Learning, in your toolbox. If you open this tab, you will see several filters. So if you have older versions of Aurora Vision Studio, like 5.0 or earlier, I think, you will not see deploy filter. You will be only able to see those filters. So if you work with the older version, if you drag and drop this filter, you will be able to open Deep Learning Editor by pressing these three dots. In Model ID, there is Model Directory. If you press them, you will go to Model Editor. That's for the older versions. What we will do right now is we will use a deploy filter. We added deploy filters to reduce the loading time of your model into the GPU and reduce the time of the first iteration. And it's easier to use deploy to access our deep learning editor. So you can go to deep learning, drag and drop deploy, and we will select detect anomalies 1. So after you insert it, you will see deploy, detect anomalies 1, and a question mark to the left of our in-model directory. So the same question mark is indicated as striped, yellow stripes here in properties. And if you press the three dots in model directory, you will see this kind of pop-up, like deep learning configuration. And here is where you can rename your model. By default, you will see numbers like model 000, model 001, and so on and so on. We can name it to model caps and press OK. And you will see the question if you want to create a new directory. And you press yes. In case you receive a pop-up that this directory already exists, you may not be able to create this model. So in that case, you can go directly to your directories and remove the model that exists, or you may rename your model. But for now, we should be able to press yes with no problems, and you will be able to see deep learning editor. Let me know if you're able to open it properly and name your models. If not, I will show it once again. Like, did you have any difficulties or? Okay. If it was okay, I will show you the first way of loading images into our editor. So the easiest one is if we have our directory of images, so caps anomaly detection, we can go to training set. We have our not OK images here, but we can either go inside of our OK directory, select all of them and drag and drop them, or we can drag and drop the whole directory. I will just drag and drop my directory, and you can see I've added all the images from OK directory. They are automatically added to our training set. You should remember that. They don't have a class yet. Not the class. Yeah, the class. I mean, OK, not OK. They're not assigned to any class yet. And all of them are selected because the background is grayed out. So right after adding them, you can press on one of the images once, and you will tick all of them as OK. If you press twice, they will be as not OK, but we want them to be correct. In anomaly detection, in theory, you don't need not OK images for the training. They are not necessary. What you need are correct OK images. But from the practice, I discovered that it's good to have them because you will see on this result analysis at the top if your score is correctly set between not OK and OK images. So you can add them. They are not used during the training because anomaly detection uses just correct images for the training, but they are good for result analysis to see whether the score was correctly set. So you can do the same with not OK images. You can also drag and drop them and press twice to label down them as incorrect. Okay. And now what we want to achieve is something you can see if you go to grayscale cropped version of our OK and not OK images. So you can compare it. Here you have a whole image, but what we want to focus on is just this part. So there are two ways to do so. First one, of course, is by pre-processing in your application. You can crop it properly and convert to grayscale. And in practice, it's the advisable way of doing so. So if you're doing your project, it's better to at least crop the image beforehand, because you can convert to grayscale here in the editor, but cropping and positioning is better to be done beforehand. But we want to achieve something similar in our editor now. So we can go to the second tab, which is region of interest. If you press it, you will see there is a rectangular frame around your image, which you can resize. And you can also notice that the frame is being resized for all the images in our dataset. You can see it on the preview of all the images on the left. If you scroll through them, and you have to just check if the object is always in our region of interest, but it seems so. So that's the first step. And we also want to convert it to grayscale, which is in our training parameters, the third one from the top. So we can select true here, but nothing changed, right? If you want to see how our pre-processing parameters affect the image, you need to select pre-processing option here. If you choose it, you can see that we have now our grayscale image. That's how the image will look like after choosing convert to grayscale option. It's very helpful, especially when you are downsizing your images. We don't have this option here, but in other models, you will be able to do so. So if you press pre-processing and downsize your image, you will see your object of interest after downsizing. You will be able to tell if this operation still leaves you with enough data to analyze and properly train your model. Okay, going back to tab 1, labeling anomalies, we can, let's say, increase our training parameters window and choose some parameters. Okay, if any of you do not have a graphic card, you should choose like the lowest sampling density, because training on a graphic card is much longer than on the training on the CPU is much longer than on the graphic card. Execution not so much. So we like improved execution on the CPU is like, I think, 4 times longer than GPU, like most of the times. But training on CPU is longer, and if you want to like check how the trainings looks like, but you only have a CPU, you can select low sampling density here. For the rest, you can choose between medium and high, depending on your GPU. Of course, you can also select low if you just want to see how the training proceeds. I will maybe go with high. Let's see how it works. And we have our feature size here. You can like make it smaller, like minimalize it. I think we can stay with the default one, or maybe increase it a little bit. Okay, let's see. We have 100 training images. It should be more than enough. But just in case, we can add some augmentations. If you go through the images, you will see that it moves a little bit So maybe we can add, let's say, 5 degrees of rotation. It seems symmetrical, but I will not risk adding flips. So I will just add a little bit of scale and maybe some noise and luminance. In some of the models, you will see that noise and luminance is already selected. So you should take a look. I mean, it should help in most of the cases, but if you don't want to have them, you can just use 0 and 0 here. After that, we have stopping conditions. You may turn them on if you want to check how they work, but it's mostly helpful if you are training for the second, third, fourth time, if you didn't find the correct parameters on the first try, and more or less know in which point you will be sure about if the model is correct or not. So I will just leave them as nil for now. And now we have to start the service. So if your service is offline, you can press and start it. And you will have information about your graphic card version of the service. You will have it all here. I will just hide it. Please don't close it, just hide this window. Okay, so if we have our training set labeled properly, region of interest adjusted, and parameters set, we can first of all save what we did for now and train our model. It's a good practice to save, because if you choose like too high parameters, maybe too if your, let's say, setup like hardware is not good enough, you may receive out of memory errors. And in that case, it's possible to just exit deep learning editor, or maybe crash your computer sometimes. So if you save your actions before training, you will not lose you adding your images and so on. It's not so important in anomaly detection because adding was really quick, but if you have to like select and label the images, like draw the features you're looking for, it's quite a lot of work, and you will not be happy after losing all of it. Yeah, but if your service is running and after you've pressed train, you will see this kind of window. You can change some chart settings if you want to only see last 5 iterations, or pan and zoom, whole progress. It's just for you to easily see everything. And if you take a look here below the training progress bar, you will see. Yeah, you probably have to wait a little bit. Oh, I know which one. If it's so, probably you have to go to task manager and kill the process because it didn't start properly. So if you go to task manager, you will see Aurora Vision Studio. And deep learning service, you can right click and kill it. Wait like a minute and you can run it after that. Or at least it's how it usually works for me. But I think I encountered it just in our like test version. I didn't see it for a long time. 5.3, but okay, just one question. Does any of you want for me to share my models with you? Because if you want, I can just upload them to the OneDrive. Hmm. Please wait. Okay, so after my training, I will share the model with you. Okay. Yeah, I mean, if you have the message, please wait, you will not see because it's trying to run. I thought it was another error. Okay, so yeah, I mean, we can go by the standard procedure. So you can like save, close everything. Yeah, save, close everything and run Studio once again. Sometimes reinstalling deep learning helps. Or did you have like the current NVIDIA drivers installed or not? Okay, if you have current drivers, yeah, because from time to time, for unknown reasons, takes sometimes longer for it to load. But usually, like closing or reinstalling works. We will have like a short break soon, so I hope that you will be able to like reinstall deep learning, and you can like repeat the steps we had here and start the service. It should be able to reconnect. Yeah, I mean, I will stop my training right now. Yeah, I wanted to tell you one thing before that. You have a validation error here below the training progress bar. If you press finish, so like stop your training by hand, you will take the best model from what you've trained so far. So even if you stop, let's say in this place when some anomaly happened and our validation error went to like here, we will not take this model in this time, but we will take the best one we've achieved so far. So I can just press finish. And after computing scores, I should be able to see the results. Yeah, if you yeah, okay, because there are two errors I'm aware of, but they are like rare. I mean, the one you had, so the service is already running. We had on our test version. I didn't see it 5.3, and clean should work. If you don't have the service running, probably reinstalling will help. Okay, if you have the same issue, I will show you how to go to log directory later. So if you have some issues with deep learning, you can send us our logs. So we will try to take a look at them. Yeah, about 5.4. I think it's like the first quarter of the next year. I think February or March, but I'm not exactly sure about the date. I mean, our aim is the first quarter, but I'm not sure about the month. Okay, I will talk about the hardware recommendations like later during a training because it's like a dead time for our training course. Okay, so you should be able to receive some results. If you choose other parameters, maybe you are able to have like 100% accuracy. I can see there is one incorrectly classified sample in my dataset. If you don't want to like use your mouse and move here to look for it, maybe you've noticed there is something like a filter just above your dataset. So if there is something wrong with your samples, you can go to filter and you can select the second from the bottom. There is incorrect classification. And filter incorrect classification. If you press it, you will be able to see the image that is incorrectly classified. Yeah, and now it depends. You probably have to change a feature size, or you can check with another sampling density. It's kind of a battle with parameters and experience because I will show you some ways to have more models trained, to not like train one, check if it's okay, and train another. But like mostly your first like 2-3 tries with the model training will not give you like the best possible results. You will have to like check for parameters, see if they are correct or not, maybe change something. Yeah. So I will just see if I have some tips on my card, if I had some good parameters written down, but I don't think so. So I will try by downsizing my feature size or using the default value and seeing what happens. But I think we can have a short break, right? Like 10 minutes for a quick coffee, something like this, and we can come back after this. If you want, you can like run your training during this break, or you can continue your current training because probably you have different graphic cards, so it may take longer or faster for you to train the model. Or you can finish your model right now and you can run another with different parameters, let's say medium sampling density and lower feature size. I will do so. And after a break, I think I will share the model with you. So if you didn't manage to train you will be able to use mine. Mm, okay, so see you again in 10 minutes. Yeah, and about the difficulties you had with service. Okay, it works for both of you. Okay, but if this doesn't work for any other of you, you can try the things I mentioned. So either killing the process, restarting Studio, or in the worst case, you can reinstall deep learning. Okay, we are still recording. If you are here, let me know by raising your hand so I can know more or less who's back. Okay, so I think more and more of you are coming back. So I will wait a little bit and first of all show you how my training went. So I will just maybe before finishing, you can see there is a third line I was talking about, the gray one. So it shows how my previous training went, and you have even added it in the previous validation error here in the history. And another thing is, if I finish right now, go to computing scores, of course, but you will be able to see this comparison. So if you are training your, let's say, second, third model, you will be given your old, or let's say current model on the left, and your new model on the right. And after the training, you can decide if you want to stay with your old model or select a new one. You can see that like everything in my new model is better. Like we have better accuracy, F1 score, precision, like misclassified images are 0, not 1. So I will choose my new model by pressing select new model here. Yeah, and as you can see in the result analysis, my confusion matrix is much better. Everything is classified correctly. And here I do not see any not okay images in my okay, let's say, sector. But telling about something more about this, this is a distribution of a score. So here the height of this bar is the number of images that have this score more or less. As you can see, most of our OK images have score of 10 point, let's say 16, 19, 18, something like this. And they are all located here. All of our not OK images are on the right side. And if we scroll down below, you can see their score is about like 35, 20 something, 40, 42. And this line that you can see here in the top right corner is a border between our correct and incorrect images. So if you drag it, you can move it if you want. And as you can see, the confusion matrix automatically adjusts to your score adjustments. If you drag just one part, you will be able to see a yellow area. And this yellow area is like uncertain or weak in case of confusion matrix. And it means that it's not sure of the result. So instead of OK, not OK, in this yellow area, you will receive not sure. So it may be useful in your inspections if you don't want to like remove all the objects. If you want to, let's say, move the objects to for the manual inspection, you might include a weak zone. So the cutoff between okay and not okay is not so harsh. You have some like middle ground where you, let's say, are checking if you can fix the object or the human has to see it see it and decide if it's okay or not okay. So you can adjust it. You can, I think it was right clicking. No, by right clicking you can edit this value. And you can also use optimize for all images if you want to go to the previous value that we had. And about the results you can see here, if you go up to the bottom and if you press through your not okay images, you will see the heat map and it indicates where the model thinks there is something wrong with the image. So if we didn't like reduce our region of interest and convert to grayscale, it could be possible for the model to focus just on on the dots in the top left corner. So you will be able to see a heat map here and maybe nothing here. So even if your scores are great, if your confusion matrix says everything goes correctly assigned, you should always take a look at heat maps to see if the model is focusing on the thing you wanted. We had one example with one feasibility study with a customer where we're checking the level of a liquid in a bottle. Basically, if there was some spill from the bottle or not. But the point is, in our data set, all the bottles which were not full had cap which was already removed, so there was no the ring below the cap. And the model was not checking like if the bottle is full or not. It was just checking if the cap was damaged or not. And that was not our point, not the point. So we had to prepare another data set to properly check whether the liquid of the level of the liquid was correct or not. So even if you have good results, you should always check your heat maps if the model is focusing on what it should be focusing. Okay. So I think I can save and exit. And I will upload my model into the directory. The easiest way to go to your directory is first do not close your directory with the model in. But if you did so, you can right click here on the bar with the name of your application, and there is option to show in Windows Explorer. And if you press so, you will go directly to your directory with your model. You can see there is my application here, AV code, AV project, AV view, and also model caps. And I will upload it into our line directory. Just give me a minute. Okay, it's there. So if you want to take a look at later, you can do so. Okay, going further, we have our model, right? We have it here. It was trained, the deploy filter. Now we want to check how it works. So it should be quite easy. We can go once again to our CAPS dataset. We have our test set here. You can see with some images. And we can drag and drop it to our acquire section. We can say set the repeat to true. And let's not put in delay for now. So we have our deploy, we have our image acquisition filter, let's say. And we also have to add a filter that will execute our model. So once again, in Toolbox, in Deep Learning tab, you can drag and drop detect anomalies. And of course, you need to connect inputs. So our image to an image and our model ID to model ID. Yeah, that's another thing about deploy filter. If you want to use the same model multiple times in your program, you can just use this deploy and connect your output, your model ID with different anomaly detection filters. Otherwise, you would have to either have a global parameter with the model loaded, or you would have to copy and paste the path to each of those deep learning filters. But we are here and we can, first of all, see on the previews how it looks like. So you can like drag and drop out image, heat map, valid, and score. And you can run the program. You will probably not run it right away. You will see a pop-up that deep learning service should not be running with during the inference phase. I can tell you that I also received this warning, but if we do not want to turn on and off the service all the time, which we'll be doing otherwise during our training, we can go to settings and change one parameter. So if you had the pop-up and you don't want to see it, you can go to Tools, Settings, and in Program Execution, there is a break when a warning occurred. So if you untick this box, you will see the warning on the console, but you will be able to easily train and execute the model. I mean, if you are using this model on the production, you should, of course, turn off the service. But if you are like trying the model, going to your application, changing something, retraining, and checking once again, it's easier to turn off the break when warning occurred box here, so you don't have to turn on and off your service all the time. Okay. Yeah, as you can see, this image is from here, so it's not monochromatic, but do we have the image from here? Just give me a minute. No. Yeah, but you can see your heat maps are focused here. And what we do is we convert it to monochromatic inside of this filter. So the analysis in this filter is on monochromatic because we convert it on the entrance. And also you don't see something like region of interest here on the input or output, but we use the region of interest that was set inside of our filter. So that's why I told you it's important to, in case of this tool, to properly locate your object, because it will be easier to like locate and crop it beforehand than adjusting region of interest after the training. When it comes to some further analysis in your program, what you will mostly use is outvalid, maybe outscore outputs, and in some cases out heatmap. And in most of the project we used anomaly detection. I think it was like the last inspection filter. So we could have some measure. I mean, it was either last or the first. So it was either like after some image processing, we had anomaly detection and it was like okay, not okay. Or it was the first in case if the detection was okay, we were doing some measurements. So that's why I told you that you will usually use out is valid. So what you will probably do is variant, something like this. So after your anomaly detection filter, you will see, let's say, variant macro filter with bool input connected with valid. And here you will have inspection in case of true and probably nothing in case of false, or you will send some data to PLC. There is something wrong with the inspection, or you will have the sending after the variant macro filter. But in most of the cases, it will look like this. I mean, if you replace this one with the camera, initialize your model and settings here, execute your model, and do some further analysis after that. Yeah, that will be it for this example. So do you have any questions regarding anomaly detection? And we'll go with the second anomaly detection example right away, but we will use the second algorithm. Okay, so just one more question. How did your training go? I mean, were you able to properly train the model in like the 10, 20 minutes of the break? Okay. I mean, the assumption we did during for the training process at least is that we should be able to more or less have the model under 15 minutes. So it's not like the information you hear that you will have to wait like 2 hours for the training to finish, or like a day or something more. We wanted to have at least in some cases first results up to the 15 minutes. So you can like finish your training after 10-15 minutes, check if the results are looking good or not. And if you think there is a need, you can continue the training later to let it retrain, or you can check the parameters and train once again. Okay. So you can create a new application or in the same one. I mean, maybe we will not use caps, but in the same one we can prepare our second anomaly detection model. We will use anomaly detection 2, and we will be working on maybe on cookies. So if we go to our dataset, you should have the fourth directory, cookies anomaly detection. If you go there, you can take a look at your training or test set, how they look like. Okay, so you can see those were the OK images. And here are the not OK ones. Yeah, but in general, this case is more like a border case, right? Because if you take a look at the OK images, I think some of them could classify, at least for me, for not OK ones, right? I'm not sure if this is like a desired or not desired outcome. So in that case, having a weak zone could be an advantage, right? But we can do the same process as before. So if you have your new program or in the current one, you can add deploy detect anomalies too. And in the same manner, go to properties and create your new model. We can name it cookies and press OK. Okay, and if you enter the editor this way, you can first take a look at the parameters. So here something changed. First of all, we have one more pre-processing parameter, which is downsample. Second thing is we don't have stopping conditions. It's because this algorithm, as the only one from what we have, doesn't have the progress window that you saw before. Here you just have a progress bar, and when it ends the training process, you will just be given the results. So that's why here you will have to focus more on your training results, on the result heat map and result analysis on the right. Okay, I taught you how to add images. In the first method was drag and dropping, but it's also possible to add files from directory. So if you don't have it open, but you know the path, you can press the first button from the left here and go to our deep learning images, cookies, and training set. Okay. Select all and open them. And as before, all of them are added. We just have to press 1 to toggle the class of our object. And we can do the same with not OK ones. As I told you, you don't need not correct images for the training. So if you want to check it, how it works without them, you can change its class or its data set from training to test. We will see how it works without our incorrect images. Okay. Now, if you have your images loaded, everything labeled, we can go to training parameters once again. And here in the, let's say, second algorithm for anomaly detection, we have two network types. At least for now, I think that for the version 5.4, we are trying to just have one of them because it gets confusing for some of our customers. I mean, in the past, we had like 6 or 7 different anomaly detection algorithms. What you see right now is like two of the best, with some improvement taken from the ones that were discarded. But we are trying to make it more simple, so probably you will see just one network type in the future version. For it, the difference between like setting parameters for single class and golden template are the parameters, because in the single class you have something similar to anomaly detection 1. So you have sampling density, so how dense we use our, let's say, feature size to crop the images. So the lower you have, the lower the seed, and the fewer, let's say, frames you have, the worse the heat maps will be worse, but your training and execution should be faster. Here you also have the depth of the network. It's the first time you see it, but it goes from 1 to 5. 3 is a default value. On the level 3, it uses, I think, all or most of its possibilities, but it's restricted by, no, it's not using all. It's using most of the important possibilities, or all important, let's say, features, or what it can use for the training, but it's not using like all of the possible memory. The higher you go with the depth of the network, the sometimes more obscure algorithms take part there, some weird mathematical, let's say, layers. But in like more difficult cases, it can help you. If you go lower, we use less powerful, let's say, we receive less powerful model, but it should be faster. And in some cases, going lower in the depth of the network will be sufficient. But if you are not sure about it, you should always start with network depth 3. In like 90% of our projects, we are using the depth 3, and it's all right. I mean, we receive great results, and we don't have to reduce or make it higher than 3. In some cases, we go 4 and 5. Here in 1 or 2 examples, I think you can go even lower, to like 2 or 1. And after that, you once again have feature size in the single class classification, which is represented by the square here. And once again, if you increase it, you can decrease it. Like the rule of thumb is it should be like between 32 and 128, more or less. So if you have to increase it like greatly to do something with it, it's probably better to increase your downsample. As you can see, by increasing or decreasing downsample, you also increase or decrease the size of the square, because the image is decreasing in size. So instead of increasing your feature size, you can stay, let's say, with something like maybe 90, but increase your downsample for the training. If you want to see how downsample affects your image, once again you can press the pre-processing button. So in the same way as convert to grayscale shows after pressing this button, downsample works in a similar way. And if you go like to 7 or 8, you will have like no information, but you can see that even going to 1 or 2 will probably still allow you to, or the model to see the difference between OK and incorrect cookies. Maybe in this case it will be harder, but if you're missing some part of it, it should be possible. Yeah, and you should try using downsample if possible. I mean, unless you don't need the model to be faster, because this parameter directly affects how fast your inference phase is. Because on smaller images, you execute your model faster. Okay, that's for single class. Another network type here is golden template. The pre-processing parameters are the same, so you can see we have downsample and convert to grayscale. But the main training parameters are a little bit different. Here you have max translation and model complexity. This complexity goes from 1 to 28. It was designed this way. That's why we are trying to remove this model from the next iteration of our software. I mean, it works great and I usually use it, but it may be confusing to some users. And we are trying to replace it with just like complexity of the model. So without the translation, like complexity from 1 to, let's say, 5 or 10, to make it easier for use. For now, we need to experiment with those parameters. What it does, like more or less, maybe you've seen golden template example with Shimon. If so, it, let's say, remembers in a similar way occurrences of some vectors in this our yellow window and how the neighborhood of our window looks like. And it after that checks if what we have here happened or in our training data set, like in a simplified way, something like this. So what you adjust here is the neighborhood of our checking window. So if we should take into account what we see around our window, and complexity of a model. So basically, the memory we can spare for it. Here, I'm usually operating in a range from 16 to 28. They are the most common values I use in my model complexity. Starting from 20 is not a bad idea. Here in translation, once again, values from 32 to up to probably 100, 120 are okay. And you can use once again downsample to help with adjusting your feature size. I will stay with golden template network type. And I think we can adjust some parameters. Maybe something like this. Check on the correct one. More or less, we can try downsample 1 or downsample 2 and smaller translation. With downsample 2 and small translation, you take a risk of this not being recognized as an error. But the model should be faster. If we go downsample 1, it should be possible to see it. I mean, you can experiment. You don't have to have the same parameters as I have. So I will probably try with the smaller downsample. Basic complexity translation 32. Maybe without grayscale conversion, because you can see that color information could help us, especially when we can see the parts of a biscuit below our chocolate. We don't have like a lot of training images, 20 of them. We use the filter. So I think we can use our augmentations. And in this case, I think we can go full with rotations, so 180, because it's like it uses both rotations clockwise and counterclockwise. So if you go to the maximum level, so 180, it goes full circle. And we can probably use also our flips, because the object is round. So flipping or rotating, it shouldn't give us any false or incorrect data in our training data set. Maybe we can add a little bit of noise. And if our service is running, we can first save and run our model. And as you can see, you don't have like the whole progress window. You have just the progress bar, which goes through 4 phases and computes score at the end. And this model should train quicker than anomaly detection 1. So we should be able to receive the results much faster, of course, depending on the parameters. But this is what I received after using downsample 2 with this translation. You can see that my heat maps are not like the nicest looking ones. They are quite big and so on. That's because of our parameters, because I have a downsample of 2, like your very small image, and feature size of this size. That's why my heat maps are not so good looking. I mean, they are focused on the correct place, But if you want them to be more accurate, you should like reduce the downsample probably. I mean, heat maps are not what's important in this model. You are more focused on the score and correct classification, but sometimes you may want to improve them. Okay, let's say I mean, if you have difficulties with a project right now, you can check our support. I mean, if you can like send us a model and images, we should be able to help you. If it does not progress at all, I will show you in a while where to get to the logs, so you can also send them to us. So I will just finish this one, and yeah, I mean, if you have any difficulties with your deep learning models, you can send us questions. That's what we are for, especially during the process right now that you are learning our tools, and of course in the future. But in the future, you will be using them effortlessly and probably just mailing about some bugs you encounter. But yeah, we are welcome to see the emails about the bugs as well, because we are not able to detect all of them, right? Sometimes customers encounter them during their projects. Yeah, going back, I will try to run the model with downsample 1 instead of 2 to see how it goes. By the way, you can always see the abort button, but if you press it, you will not just stop the model, you will stop without saving. So it's better to press finish if you want to do so. Okay, I have the comparison between my old and the new. I mean, the results are close to the same. There are more details if I want to take a look at training time. You can see the training parameters. If you press this plus button, like how long did the training took, but I think there is something wrong with it. It was not like 2 seconds. It was quick, but that's so quick. Okay, and let's say I want to select my new model. So I press this button here, and you can see the heat maps look much better. But the results are the same. So if you are more focused on the results, like true, false, there is no need for you to go to downsample 1, or you can go to downsample 2. You don't need to like retrain the model once again with those parameters because you already had them. So if you have like 2, 3, 4 models, you know that the one you want to use was like some of the previous ones. You can use model history to access them. Okay, so if you press this button at the bottom, there is model history. Here is version 2, total size of all your models. If you press this arrow, you can see I have my model history opened. So if you press it, you will see this. You can like switch between versions to see the comparison here, but the score in both of them is the same. You can right-click and press compare models to see the same details you saw after the end of the training. And if you want to switch to your old model, you can right-click and press switch to this model. If you do so, you will close the editor briefly and open your old model once again. You can see my settings went to the state in which they were during my first model creation. And if I don't need my model with downsample 1, because I think this one works great, I can right-click and remove it. And you can see the total size of my models went down by the size of the removed model. I can just close it, save, and this will be my working model right now. Yeah, and once again, if you save and exit, you have to proceed in a similar way. So I will just disable those filters, and I will add my test set once again. And from deep learning, detect anomalies too, and connect everything. And important outputs are the same as in the first anomaly detection filter. So you will be focusing on out is valid and out score to see how your, maybe I will slow it down, to see how it went. Heatmaps just indicates when where the model was focusing on, so I can just turn it off, and you can take a look at the score and the images. So that's like the first. Okay, that's the first way you can analyze your data set, your images. So you can train your model on a training set, save everything, close the editor, and do some analysis here, right? You can load your test images, run your model, check how it goes. It may be good if you have, like, let's say 10, 20 images, you can like iterate one after another to see, this one is false. Let's say the heatmaps focuses this part, so maybe there is some kind of crack here. If you have like names of the file with OK, not OK, it could also help you with judging whether this cookie was correctly classified or not. So that's one way of doing so. Another way is, or useful one, I guess, adding your test dataset into the editor. So if you like add your test dataset into editor, you can check the statistics of your test set directly there, which in case of like bigger data sets, more important projects, is the way to go. This one is like for the quick look, and the like more proper approach is doing it with deep learning editor. One case in which I don't recommend adding more images there is probably if you have some memory issues. So if you have some memory issues, it usually happens, at least it happened. It usually happens in the newest version at the end of your training. So if you have your model trained already, once again, Memory issues may happen in two places, basically. So during your training, if you've selected like too high complexity of your model, or you didn't use downsample and the image is like 12 or I don't know 25 megapixels and you have like 200 of those images, maybe something with memory issues may happen. And other places after the training, when it classifies all your images and computes the scores, that's the second place in which you can encounter memory issues. So if you encounter them and you have your test set among your images in the editor, it could be a good idea to remove those test set to have your model compute everything correctly. Yeah, but usually it happens when you have like the depth 5 zero downsample and the very big images, or like older GPUs with like close to no memory on it. But yeah, you can try doing so if you encounter those difficulties. Okay, yeah, the answer to the question is maybe, or it depends. Like in all of the projects, I mean, I don't have your images. I cannot see how the defects look like. But the next topic, which is feature detection, may be the answer to your question. Yeah, but one second, if you have some images and you can send them to us or like sign the NDA, so we can like take a look and advise you. But I will introduce feature detection to you. So if the error always looked the same, maybe feature detection is a way for you to solve it. So I will just save it. And I will start with the quick presentation once again, but we will quickly go. Unless you have some other questions like about this topic. Okay, I don't see any. Okay, so the next deep learning model we will be focusing on is feature detection. So, timer here. And as the name suggests, it's not exactly only for detecting defects, but also features. And that's how we use it. We use like both ways, capabilities of this model. So one way, of course, is to check for, let's say, cracks, scratches, and so on the image. And another way is to look for some characteristic parts or parts of the image, let's say, we don't want to analyze, detect them, and let's say remove from the analysis. Or we are looking for, I had a project, I was looking for the stalk of a plant. So with feature detection, I was looking just for the stalks and was checking for the mass center of the stalk. And with like traditional machine vision algorithm, like with, let's say, thresholding by color or or something else. I mean, thresholding was like impossible. By thresholding, we could like separate the whole plant because the stalk and leaves were of the same color. But we had to use something more to detect just the stalks and do some analysis on them. So the stalk itself was not a defect; it was a feature, and that's how we used feature detection for this project. From like it's a supervised training, and supervised means you have to provide more data than just okay, not okay, like in the anomaly detection. Here you will be either drawing masks or you can import them. I will show you in the second example how to import and in what way the data needs to be prepared to import the masks. Also, I will show you a trick how to properly like label like 100 images. It will be very useful because labeling is like the most tiring part of the model training. It's like you see the progress, but just by drawing the mask. So if you can like omit or make it faster, it's always a good idea to use tools for it. The second point is we can have multiple classes of features. So in anomaly detection, you only had like, let's say, one classification, good or not good. Here you can have like a stalk of a plant, petals, leaves, a background as a class. You can annotate different features or defects on the image, and you will receive the output of this deep learning. As the output, you will receive heat maps of each class separately. So let's say the first class will be your background, the second will be, let's say, the robotic arm, for example, or like a part you want to detect. The third will be something else. Yeah, and the third point is like the how to use it. So it's for finding features that appeared on the image. So you need to know how something looks like because you need to annotate it to draw its region for the model to train on this data. Yeah, that's why this point is 4. In anomaly detection, you just were giving okay data and the defects that would appear would be like select as not okay. Here you need to specify what you are looking for. The training overview is the same with some slight differences in terms of region of interest. The menu you will see is also the same. Training parameters differ a little bit, and you will see a little bit different result analysis. Yeah, in case of region of interest, you can see that the region of interest may be unique. So the region is selected here on this image, but you can see that on the second and third image, there is no region of interest selection yet. So it helps if you want to reduce your workload, like if there were like 2 objects here, but you only want to select and annotate one, you can reduce the region of interest and just annotate this one object. If you only want to annotate one of 2 faulty objects, please do so. Please do reduce the region of interest, because if you do not reduce the region of interest and only annotate one of 2, let's say, objects on the image, you will like confuse the model, because you as the user have to annotate every feature correctly. So you cannot like leave some annotated features on the image because it will provide false data to your network. So if you have to choose between annotating 10 images correctly or 100 like so, annotate 10 images correctly. It's a better way to develop your model, and with a trick I will show you in a minute. 10 images annotated correctly can annotate and help you annotate the 100 images you have in your dataset. When it comes to parameters, here you are working on the depth of the network and the patch or feature size. It depends. The name depends on the version you're using. Also, you have grayscale conversion and downsampling. The augmentations are the same in all of our models, but here you have stopping conditions. I think by default, validation accuracy set to 99.9% is ticked, but you can of course untick it if you want. And as for the training process, you will see training progress window with accuracy on this axis. So the higher you go, the closer you are to the top, the better should be your results. And the same as before, instead of best validation error, you have best validation accuracy here. So even if your validation accuracy lowers a little bit, we will take the best parameters of the model we've trained so far. Here on the right, you have result analysis, and there is F1 graph here. As you saw on the introduction presentation, the closer we are to the top right, the better. If you want some other graphs drawn on this window, you can select them with the cog icon here on the bottom right. And also you have general parameters like precision recall F1 here on your current image, all of the images, and images of your test set. Important notice is you can add images of your test set without annotating them. It's like good and bad at the same time. I mean, you can do it because it doesn't affect your training, but you will see a drop here, graph, and you will see a drop in your parameter scores. If you also annotate them, you will see like proper results on your test set. So to see like proper result analysis on your test set, you have to also annotate your test set. But you can just add them to see how the heat maps look like. You don't always have to look at result analysis. This bar here is for your threshold setting. So if you think your threshold is set too high or too low, you can increase or decrease it. Sometimes I think this error was reduced or removed completely, but in some cases, your threshold bar will go to up to 255, and you will see like no heat maps here. So in that case, like lower your threshold levels, like 100, 120, and you should be able to see it. From time to time, it happens after the training. It's the image with the answers, a shame. Yeah, about some use cases. This one was for checking cardboard pieces among some kind of tea or tea leaves. and another one was for checking cracks on eggs. So in both cases, we knew what the defects was like. So cardboard here and some cracks here. We were able to draw it and annotate or draw and use it for the training. So which example should we go for? Just give me a minute. Because we have satellite, but it's better for showing you how exporting and importing works. So we can do it after that. Let's see. Not this one, this big images, maybe threads. It could be, yeah, it's here. Yes, so this is the one you saw on the presentation. So if you go to the bottom of your training set, you can go to thread feature detection, and let's say we can go to our training set here. If you double click, you will be able to see the objects we are going to check. And you can see the defects here and there. Or no defects at all. Okay, so I think we can use it for now. So we can, let's say, prepare a new program. Let's say that detection directory, and I will name it feature detection. Okay, so we have it saved. So yeah, the procedure is once again the same. So you can drag and drop your deploy filter to the initialize section and select detect features. And once again, in properties, in the striped field, press three dots, and you can call it model threads. And if you press OK, you'll see a similar view as before. And you can add images either by drag and dropping or with the add images from directory, whichever method suits you best. I will add my training set first. And after that, I will add my test set as well. Just remember to press here to change your loaded images from training to test set. Yeah, also a tip, if you are annotating a model and you don't want to annotate more images, you can like move them to your test set from the training. They will stay in the same place, so if you want to move them again to your train set, you can do so. I mean, it's to like reduce the workload because of the trick I will show you in a minute. But in general, all your training images should belong to your training set. So so please remember to like go back with them to your training set. Yeah. So now we don't think about training parameters for a little bit. We are focused on this bar here. They are tools for annotating. You have, of course, eraser here, brush, and some regions you can draw. The one I use the most is probably brush, and one of the two you can see here. So either polygonal, when you can just press in some points, and after double clicking, it will like annotate the whole region. It's clear. Or freehand region, so you can like draw a shape that you want, and it will also annotate as this one. For the brush and eraser, if you hold Control button and move your mouse wheel, you will see that the size of the brush increases. Same works with the eraser. Or you can do it by hand here with the size change. Yeah, so now a task for you to annotate some of the images. I think we can annotate, let's say 1, 2, 3. Let's annotate the 3 or 4 without the hand one. So 1, 2, 3, and 4. If you have monitors of different resolution, like me right now, you will see that the size of your brush is not the same as the size of the graphical representation, as you can see. So be aware of that. Also, keyboard shortcuts work here. So if you draw something and press Ctrl Z, you will be able to remove your last entry. And of course, you should remember to expect the results similar to annotations you've done on the image. So if you do it like precise and good, your results should be, your heat map results should be more adjusted to what you expect. If you do it with some error margin, the heat maps probably will not be as accurate as you want. And also, once again, try not to miss any of the errors on the images. Yeah, in theory, you should be accurate. I mean, not like the pixel kind of precision, right? I mean, you can, and I advise you to be like pixel accurate, but it's usually not humanly possible to be. Also, my defects are quite big, so even if I miss like some of the pixels here, is not so important. But yeah, try to be accurate. at least for your projects. For the training, you can do some less accurate annotating. I mean, you can do something like this. The model will still show you the results, right? It's not like it will not show you, but you will probably see some noises here and there. So yeah, if you select like me right now, so not so accurate, it will still work, but the probability of some random noise and being a little less accurate is much higher. You need to like find a difference between doing it quickly and accurately. That's why I told you it's like the most boring part of using deep learning, but also like the most time consuming. Unless you have someone to help you with annotating, it can take a lot of your time. And if you want to check, you can like do something like the big blobs. You can try doing annotating like this to see what kind of results you will receive. I think I always tried like the smaller blobs with this example, or even when we are preparing it. But for the comparison, you can check how bigger blobs work. Okay, I'm done with the work. I mean, I annotated my first 4 images. And for now, I will, let's say, move the rest to my test set, at least for now. I will give you some more time to finish. But as you can see, it's not like a fun process. But nevertheless, it's an important one, right? Because you are preparing your data set and you are affecting your results more or less. And if you like fix some of the annotation, maybe your results will improve, right? If I remove correct parts of my image from the annotation, the accuracy should improve. Because what you can see, I mean, you have like feature 1, is not all the feature or classes we have, because by default we have one more class in our training than you can see. Here, the feature 1 is what we draw or annotate, and the hidden feature is like anything else. Anything which is not a feature is also a class. It helps with the training. Okay, so if you have some of the images annotated, like, I don't know, 2, 3, 4, at least 2, you can move the rest of them for now to your test set. You can like select them with Control, or you can press the first one, Shift, and the last one, and change from train to test. Or you can go one by one and change them to your test set. Okay, so if you've moved the rest of your images from training to test, and you have some images annotated, you can take a look here. In the middle, right above your preview, there is the auto label feature. It will not work right now because if you go to an annotated image and press auto label, you will receive this pop-up window. So you cannot perform automatic marking because you do not have a model trained. So it indicates that if we have a trained model, we will be able to automatically label the rest of our images. And that's what we are going to do. So we have like 4 images. I mean, for it to work in a better way, I advise you to have like 10 of the images properly annotated. But right now we can check how it works with 4. The bare minimum is 2. It works for all of our models. I mean, you have to have at least 2 images for the training to run, because you need one for the training set, for the training, and the second image for the validation. In case of classification of object, will be later, you need at least 2 images for a class. Okay, but going back, if we have our 4 images, we can go to training parameters. Okay, let's see how preprocessing works. Maybe we can go to monochromatic and see how downsample works. Right now, my heat maps are like obstructing my view. Maybe you can see it. So if I don't want to look at them, it's possible to turn them off just to see the preview of my object. If you go here, there is something like single class. You can change this option to no classes. Or if you have more classes, you can use all classes here also as well. I will choose no classes, and you can see I can see my defects, but the markings didn't disappear. I mean, if I turn them on again, I can see them. Okay, so let's say I will stay with patch size of 96, dump sample 2. I should be able to see my defects. And because we have only 4 training images, we should increase our augmentations by adding rotations, flips. Maybe a little bit of scale. Something that will increase our training dataset. Okay, and once we have our images annotated and parameters adjusted, we can start with the training. Before that, you can go here to the bottom left. You can see in this model, validation accuracy 99.9 is automatically selected as a stopping condition. So If you reach it during your training, the training will stop and save your model. If you want, you can, let's say, select also a time condition, let's say 5 minutes. I will select a lower value to just show you. You can select a higher one if you want to see how it works. I will save it just in case and press train. And once again, you can see a training progress window, and you will see the accuracy. You should see the accuracy go up. If it's going down, it's not something you want to look at. After annotating like 4 images, we shouldn't expect wonders or very high validation accuracy, but let's see how it goes. Yeah, this kind of fluctuations happen usually at the beginning, but you probably remember from anomaly detection, you sometimes from time to time the random places, like let's say 10th or 20th iteration. But your graph will look like this more or less for the first 5-10 iterations. And if you have a good data set, good labeling, it should smooth here up to 21 and be quite good later if you want to continue your training. Let's see, I hit my 2 minutes mark. So after this iteration, my training should stop and it should calculate all the results. Yeah, as you can see, I went above my 2 minutes time limit, and that's why it's computing scores right now. It stopped the training. And what happens? What I told you. Sometimes when you finish your training, probably when you don't have much data, the threshold level will go to the maximum value, and you have to lower it by hand. 4 images is not so bad. When you can continue with your training, you don't have to stop like I did. I did it for you too, so you can see some of the results. And I will go through my test set to show you the results on another parts that we have. So you can see they are not ideal. There are some noises, but more or less here, more or less in correct places. But you can also notice that on the right, in the result analysis box, current image has like 0 in all the statistics, and test set also has 0. And also all images is impacted by lack of annotations in our test set, because all images is calculated from all of the images. That's why the values are lower. And of course, our F1 curve is not so good looking. If your training accuracy reached like, let's say 90%, 80 something, you can probably stop the training because you have like 4 images, so it will not be super accurate right now, but I wanted to show you the trick I described earlier. So if we select our 4 images right now, right, we have the model trained. I've selected my 4 images, which were in the training set. I can change it to train set once again. And now, instead of annotating them, I can label them automatically. So I can go to labeling features from the result analysis. So to the step 1 once again. And here on the right, there is the auto label button. If you press it with those 4 images selected, you will see, at least for the first time, this kind of window. So we can select threshold level. Let's say we will stay with like 150. And also region opening. You shouldn't change that. I mean, you can, but you will reduce maybe 1 will help, or 2 if you want to reduce some weird noises somewhere on the image, but usually you should operate with just threshold level. And if you have that, like after clicking auto label, after selecting those 4 images, you can save and label. And you can see the feature 1 is labeled on my images. That's why I was talking about correctly annotating 10 images rather than so annotating 100, because if you have 10 images correctly annotated, you can train the model on them and use them to annotate the rest of your images. It's really helpful and saves time. You just need to remember to go through them and fix some mistakes, because they will happen. So as here you can see, it missed some of the points. I think that should be marked as defects. And also we have some false annotations here, which you should clear. But usually like clearing and fixing 1 or 2 errors is much easier than, or faster at least, than annotating the whole image. Okay, should I show some of the steps once again? Okay. Okay, so another option is to auto-label. There should be one to auto-label all. I think it disappeared somewhere. But basically, if you select all the images, you can auto-label all of them. You can do so. I mean, you will see at least some improvement on your test set results. So you can go to Filter, select Test Images, and press Ctrl-A to select all of them. And now if you auto-label, your test set will also be labeled after a few seconds. You can see it's not a great labeling right now, but it will be used just to see how our test set results behave or are shown. Okay, going back. Now we have 8 images annotated, and assuming that our training parameters are correct, or we can reduce, let's say, brightness and noise, we can train once again, or if you do not change your parameters, you should be able to resume. I will try to press this button, should be possible. Yes. Okay. So what I did right now is I pressed the resume button. So it may happen that the graph is not going exactly as you wanted it to, but not exactly bad. And you want to check what's wrong with it. You can manually finish by pressing the finish button to see your current results. And if you want, you can add more images to your training set. What we did, right? We had 4 training images. We've added another 4 there. As long as you don't change your main training parameters, or you don't remove images from your training set, I think it's all. Maybe there was also something with region of interest, but definitely removing images and changing your main training parameters will not allow you to resume your training. But if you just add new annotated images, or if you change some of the augmentations, you should be able to resume your training. And you will resume from more or less the place you finished before. It will need like 2 or 3 iterations to go to your previous level usually. But it's a good method if you don't want to start from the beginning, if you think it's taking too long. Okay. I will finish it for now. And you can see the same comparison window. You can see or expand the data to see the statistics on all the images. And here you can see even like not exactly well labeled test images give you more images, more input than not labeled ones. So you can see some of the parameters, at least like the threshold adjusted is much better than the previous one. We can select a new model and see how the result looks like. I mean, you can train a little bit longer if you want. You can just take a look at my screen for now. If you want to compare your labeling to the heat maps, you can use the labels button. It's just right to the heat map button here. If you press labels, you will see how your features were selected. And I think we have such a good fit here because it was now a training set, right? Yeah. So I need to clear it up later because you shouldn't, like I told you, you shouldn't have the same object in your training and test set, and we definitely have the same object in our training and test set. So probably that's why the results here are good, but the object should not be here. I think I changed it properly some time ago, but probably I didn't like switch the data sets here. Yes, so here you can see what happens if you have the same object in training and test set. So yeah, the results are great, but if we move to something that was not there, you will see they are not so good. Let's repeat it once again, and need some more training or more data to be better. Yeah, so you can learn from it what happens when you have repetitive data between sets. So you will see great results, and after that, if you run it on production, it will be like this. So try not to repeat this error. Yeah, but basically this is how you can make your work easier. If you annotate correctly, like 10 images, train your model, you can after that annotate the rest of your images with some fixing, of course, some removing or adding more annotations. Okay. Do you have any questions about feature detection for now, at least? After the break, we will do another example where I will show you how exporting and importing works. Okay. I don't see any questions. So how long do you want the break? Like 40 minutes? How long was it with Shimon, and was it enough? Okay, so I will see you again in 40 minutes. I will stop the recording. So if I do not start it after our break, please remind me to do so, because we want to have the recordings. I mean, probably you want to have them, so you can go back to them and check something later on.